Hello, gentle readers. Ross Finlayson here. November 8, 2025, for Reading Foundations today. Box 1 is rather read through a little bit, and today then I'll just be leafing through a few of these loose books piled around and just read us from their inspirations, reflections on what here is about the theory of everything, a theory, the theatheory, as an aspect of theory, a theory of everything, a logical or technical approach. Then what we'll hope to do today is get into box 2, this next box of books, and just see what's there. And reflect on that it's so difficult to read thoroughly all these many works in mathematics and logic and physics and science. Yet they can be read together. And the idea is gain a familiarization with the language of science, and the language of mathematics, so that thusly via exposure to the concepts and the necessary fitting together of a language, at least. Some people will say, like Worf the linguist says, it's like, well, no two people have the same language, forget about it. At the same time, it's like, well, mathematics sort of is one language. And then the etymology for English kind of is one language, and it changes. It's dynamism and its fluidity over time, yet represents its comprehensive course, the discourse. So it's just something that will be just more of these sort of unstructured, unscripted readings that may, one hopes, serve to introduce some ideas for people interested in foundations. And then for me, it's just kind of a grab bag assortment of for posterity, what would result sort of just some cultural material. Well, let's see here what I have today. Well, here's the loose stack first. So this first book off the top is from this. It's a series called the Harvard Classics 5-foot shelf of books, and it says Faraday, Helmholtz, Kelvin, and Newcomb, etc. So Faraday is the great electrician, and there's Faraday law and these kinds of things. And Helmholtz gets involved with a lot of the things that are the non-standard, like the Helmholtz layer, and with regards to the spiral wave and the wave spiral. So for the Maxwell, we get the whole E cross B bit, and then that's about the moving charges and moving fields. The electrical and magnetic fields, as they're usually given to be. And then the Faraday makes for like the integral about the circuit and these kinds of things, vis-a-vis Ohm's law and Kirchhoff's law for passive and active electrical circuits, which very, very well has a model as of liquids like water, same kinds of ideas as voltage or for a potential difference as what's the potential for pressure, and then Ampere's current and these kinds of things. That the notion that electricity flows like as a fluid, it has a fluid model, and it's a lot like liquids, our usual Newtonian or compressible and incompressible liquids, usually incompressible being the idea, and then similarly for the electricity, then has that where those things meet, the fluid models for liquids and electricity, then also they fall apart, because electricity's got the skin effect. It seems to go mostly on the edges, whereas liquids have the core effect. Their flow is mostly in the center, in the middle of the course of the passage in the medium, the fluid. So the idea then that these thinkers helped reflect, first of all, back in the 1800s, that electricity, which is invisible, yet can so be established to be like so, and then mathematically and be like so. How's it? I just thought to take a look at this. When I found this book, I was like, oh, good. I want to know more about Faraday, and then also Helmholtz now, because Helmholtz is seeming more apropos, kind of like Larmor is, and then it also has some writings from Kelvin, and I don't know much about Newcomb, and so that's something to get figured out. Newcomb. And then it's from the Harvard classics. It's got that veritas, truth is the idea of what that's supposed to intend to entail. And then it's plastered all over it here, the front of it, veritas and all that kind of stuff. That I got this book as from a library, Friends of the Library bit. So it's got a picture of Faraday here. And then let's see what are some of these titles of these things. Contents, the forces of matter. And so this was one of these Christmas holiday things over in Great Britain at the Royal Institution in 1859 and 60. The force of gravitation. Gravitation, cohesion, chemical affinity and heat, magnetism, electricity, and the correlation of the physical forces. So that's also regards to like the magnet and the electret. Two different kinds of things. One about magnetic force, one about static electricity. The chemical history of a candle, talking about combustion and the theory of combustion and these kinds of things. On the conservation of force. So this is introduced to a series of lectures delivered at Karlsruhe in the winter of 1862, page 173. So that'd be relevant with regards to things like least action and conservation law. And the energy in the entelechy and about creation and destruction, that nothing can be truly created or destroyed. It's just conserved overall. So that might be kind of a relevant thing. And so this is all by Michael Faraday. Then into the wave theory of light and the tides. The extent of the universe. That's something else to be looked at. So just briefly, to take a look to on the conservation of force by Faraday. As I have undertaken to deliver here a series of lectures, I think the best way in which I can discharge that duty will be to bring before you by means of a suitable example some view of the special character of those sciences to the study of which I devoted myself. Natural sciences, partly in consequence of their practical applications and partly from their intellectual influence on the last 4 centuries, have so profoundly and with such increasing rapidity transformed all the relations of the life of civilized nations. They have given these nations such increase of riches, of enjoyment of life, of the preservation of health, of means of industrial and of social intercourse, and even such increase of political power that every educated man who tries to understand the forces at work in the world in which he is living, even if he does not wish to enter upon the study of a special science, must have some interest in that particular kind of mental labor which works and acts in the sciences in question. Well, that's nice, I suppose. Characteristic differences which exist between the natural and the mental sciences as regards this kind of scientific work. Mental life, the influences are so interwoven that any definite sequence can but seldom be demonstrated. In nature, the converse is the case. It has been possible to discover the law of the origin and progress of many enormously extended series of natural phenomena with such accuracy and completeness that we can predict their future occurrence with the greatest certainty, or in cases in which we have power over the conditions under which they occur, we can direct them just according to our will. So this is the usual idea of the lever, that the power of intelligence makes for mental lever, and so with regards to then other ideas of entropy and organization, then there's all such manners of the juxtaposition of forces, and then the balance of those and the adjustment as via the lever and the application of advantage. And before getting into things like informational advantage in game theory and that kind of stuff, and duplicitousness, as an example in game theory of the application of misadvantage. And then also, without getting too much in the ideas of systems which actually endeavor to get the worst case behavior out of something, meaning by that to get the most disadvantage. That sometimes taking the most disadvantage is when you have to trade off otherwise resources that you could totally lever for like great advantage, but actually the resources are more of a cost than another resource. Like, for example, trading height for tension in a spring to store energy as according to gravity, while yet levering leveraging pulleys to get the least sort of advantage from that, because the height is at more of a cost than the rolls of the pulleys or something like that. Well, then to recover that energy stored as an example of a thing. It's, for an example, like a 10,000 to 1 pulley block, and then being able to use that as a store of energy and something like that. Is just about then the balances of things, the conservation of law on the conservation of force. On this exact conformity with law depends also the certainty with which we know how to tame the impetuous force of steam and make it the obedient servant of our wants. On this conformity depends, moreover, the intellectual fascination which chains the physicist to his subjects. So causality is inviolable. It is, by definition. Causality is not violable. It is inviolable. We continually find points of contact comparison in our conceptions and feelings. We get to know the hidden capacities and desires of the mind, which in the ordinary peaceful course of civilized life remain unawakened. Now, I don't know about that, because everybody's always thinking about something, but these are kind of like the greater extended efforts. So, and then Faraday says, you got to want it, and you should. Reason, we call that faculty innate in us of discovering laws and applying them with thought. Reason. Last decades of scientific development, this law is the law of the conservation of force, a term the meaning of which I must first explain. It is not absolutely new. For individual domains of natural phenomena, it was enunciated by Newton and Daniel Bernoulli, and Rumford and Humphrey Davy have recognized distinct features of its presence in the laws of heat. So there was Joule and Newcomb and these kinds of ideas. We talked here a lot about Fourier, and with regards to Maupertuis and least action and these kinds of things. But the conservation. So this is before, like, Noether's theorem and invariant theory and stuff like that, but it was already quite in place. The possibility that it was of universal application was first stated by Dr. Julius Robert Mayer, a Schwabian physicist now living at Heilbronn in the year 1842, almost simultaneous with, independently of him, James Prescott Joule, an English manufacturer. So energy is joules, right? So that's just not an unusual thing. As regards to joules and newtons and energy and work and power and these kinds of things. An English manufacturer made a series of important and difficult experiments on the relation of heat to mechanical force, which supplied the chief points which the comparison of new theory with experiments was still wanting. The law in question asserts that the quantity of force which can be brought into action in the whole of nature is unchangeable, can neither be increased nor diminished. My first object will be to explain to you what is understood by quantity of force, or as the same idea is more popularly expressed with reference to its technical application, which what we call amount of work in the mechanical sense of the word. So these days that's all kind of framed in terms of energy, and some people say, well, that's instead just momentum. But momentum is changing around a lot and all the time, and energy is generally considered to be conserved, and then the entelechy. And then force is with regards to the application thereof, and with regards to Lagrange and the severe abstraction, and what's to be real and what's to be fictional, yet together they must be always balanced out. Here that it's overall a potentialistic theory, and then even then finally the lines of force are just kind of a last inner scalar product of this projection of the potentials in theory. There's really potentials in power, the dunamis and dynamis, that being kind of one word in Greek, potential and power for the energy and entelechy. And then that for this energy, then as it's kind of like from the last talk, then we get like into the F fields and the F forces, meaning Faraday here, and Fresnel and Fatio and Fizeau and Fitzgerald and Finley Freundlich and these sorts types. And there's another couple that kind of fit. So for forces and fields, they're all related by energy, kind of as like a U for Einstein, a bunch of F's for forces and fields, because then abstractly, energy doesn't even exist as a pure energy. And so it's always one of these other forms. And so the conservation of forces like so, but then the conservation energy is usually attained. And it helps describe that Joule and Meyer kind of come up with this. And then later Noether has this also, it's invariant theory and makes for symmetries. Because Noether's law is that for any invariance there's a symmetry. So for any symmetry there's a conservation. It's a very algebraic sort of treatment then to so follow, yet as well can be seen as kind of a reduction when we still have to deal with like world's turn and the unlinear to result way, way, way up above that, the nonlinear, and we result on top of all that, the superlinear again, to help express that things like turbulence and flow and flux and shear and the transverse all somehow live together in a continuous world with regards to these spiral waves and wave spirals of electricity and magnetic fields and their creation or formation and dissipation, all the things. Talks about machines. Talks about the expenditure force. And then, of course, this is all since the ancient Greeks, and the ideas of power and resistance, and like, as you're considered from the Mertonian school, 100 years before Galileo, that 100 years before Newton. And then here for the Newton's zeroth laws for Einstein's attack on Newton after Einstein's defense of Newton. The idea that there's a central symmetry is formally unlinear, the account, which is otherwise that the classical laws are linear and pointwise, but nothing really is. So it's at some point in time, it's the sphere abstraction to the mechanical reduction, as this account makes, ends. And then he talks about gravity a bit. And then, so he's just talking about that everything's connected, and it's continuum mechanics. And then getting into ideas like of mechanics like flywheels and overshot wheels and the ideas of taking up the slack and these kinds of things and smoothing the things, pulleys, machines, cranks, pulleys, gears, wheels, water wheels, pendulum, on the conservation of force. Now getting into Helmholtz here, then and we have something. Oh, if that was Helmholtz on the conservation of force. My apology. See, this was just read off. It didn't have the author there in the table of contents. So Helmholtz has got this great thing on the conservation of force, and I'll be looking at him here to see. This we can do the 8 of the currents of electricity, because this is what I want to read up from about Helmholtz is about electricity. Bubbles and electrolyzation. Combustion of those products. Here become acquainted with a new source of work, the electric current which decomposes water. So electrolysis, the electrical lysis breaking of water into hydrogen and oxygen, can also be kind of applied to carbon dioxide. And so then you got a bunch of carbon and oxygen and hydrogen, and you can kind of relate that to some calcium carbonate and some hydrochloric acid and a bit of a reactor setup, and the input products are those things and electricity, and the output is hydrocarbons like liquid fuels. So it's well known, and you can find many, many examples discussing it over the past 10 or 15 years ago at least. It's not just like the Fisher-Tropsch process. It's like we can liquefact coal and make it so that we can have all the liquid fuel we want out of coal. It's like, well, yeah, but now for $15 a gallon or so, you can make liquid fuel from these products, which are available by the train car load, and if not, for example, just right directly from the air is carbon dioxide and rain. So that's just these are things they were discovering then, and now it's like, well, yeah, if the prices kind of equilibrate, then that would be a renewable source of carbon neutral, sustainable aviation fuel from the electrolysis of water and carbon dioxide. And it can be stored, the carbon can be stored using calcium carbonate to put it in basically a room temperature storage, which is carbon store. And then with the sulfuric acid, similarly for the hydrogen, and then putting that back together and making a pretty simple way without really needing nanomaterials or some kind of unavailable type things for these kinds of simple ways to result Basically, that a small solar panel could produce a few ounces of fuel a day just by sitting there. These are usual things. Electrical currents can perform work, but to keep them up, we must consume either chemical or mechanical forces or heat. Or this is just expressing that overall energy is conserved. We may express this generally. It is universal character of all known natural forces that their capacity for work is exhausted in the degree in which they actually perform work. In a closed system. In physics, we have to then get into the ideas of the open and closed systems, and then why waves are these things is the usual idea of change, model of change in an open system. That's according to motion, and you can read that from the moment in motion bit. These are the kinds of things. So yeah, Helmholtz is going on about. I'd be looking, and he's talking about ice and glaciers, and so these be considered stores of energy. Like one of the greatest stores of electricity is just like pump the water uphill, let it sit. When you need electricity, run it back down through a dynamo. Hydropower. Glaciers. Helmholtz. Then this gets into Kelvin on the wave theory of light. So you'd normally think of Kelvin with regards to the thermodynamic laws, but here's talking about the wave theory of light. So that's often related to Huygens, the Huygens principle, and there's multiple Huygens principles. One is about diffraction and refraction, but the other one is like waves make waves. So it's just another continuity postulate or principle. And Helmholtz, he's casting some shade on some English minister. He's talking about the wavelength of sound. So, yeah, the wavelength and the wave theory of light is like, well, we got an acoustic model of waves, first in water waves and fluid and liquid medium, and then it's like, well, we're using that for sound too, and then we get into Mach and stuff like that, and why about the attenuation and dissipation of the oscillation and restitution, so waves, and so Kelvin here is talking about waves in sound as that's after basically waves in ponds. So that's why waves are so great, because they're accessible. And then just like the fluid model of electricity and water or liquids is different, then also the wave model gets involved. And then for the spiral waves here, it's like, well, we got to attach something to waves. And it's like, well, how about waves? And for Helmholtz equation, wave make waves in a spiral. That's nominally small, yet it keeps things going around. One thing we're sure of, and that is the reality and substantiability of the luminiferous ether. So this is about ether, and it's like, then that's just like the absolute space exists, and so magnetic fields live in it. But they're all moving by moving frames, and so we look to O.W. Richardson for like 50 or 60 years after this, like much more about that. And then there's a great debate about the non-existence of the ether, after Michelson-Morley particularly, which is kind of like at a moment, but it's not allowed to turn around or move, and it's not really moved because then it wouldn't be still and you couldn't get a reading off it. But it does. That then Einstein as well, he at some point in time he's like, yeah, I know that that the ether existence is not part of relativity theory, and we can't say it's so, and some experiments to validate by a Lorentzian this way or that way say it's not so, yet me and Infeld here say it's so, or I do by myself in Sidelights and Relativity, which you can read now 100 years later, or 85 or 100 years later. So Kelvin is like, well, this is so, it's indubitable. This is his thing about, that lights and electricities and magnetic things are invisible, but they got to be somewhere. Oh, this is a kind of great quote about the finitude and infinitude. Because, usually the idea is like, well, it's all got to be finite and add up. We have the ultraviolet catastrophe. It's got to add up, or we have nothing to add up. Okay. And then the infinite is like, what is the infinite? It's like, it doesn't exist. But here's what Kelvin says. I say finitude is incomprehensible. The infinite in the universe is comprehensible. Now apply a little logic to this. Is the negation of infinitude incomprehensible? What would you think of a universe in which you could travel 1/10 or 1,000 miles or even to California and then find it come to an end? Can you suppose an end of matter, an end of space? The idea is incomprehensible. Even if we were to go millions and millions of miles, the idea of coming to an end is incomprehensible. You can understand 1,000 per second as easy as you can understand 1 per second. Or here it's like, seconds per one, the meters per second or seconds per meter. You can go from 1 to 10 and 10 times 10 and then to 1,000 without taxing your understanding, and then you can go on to 1,000 million or million million. You can all understand it. So he's saying that it's infinite, and then there's the infinite variability of the frequency of, or the wavelength of light, because it's not discrete. The wavelength in that of light, although it's just figured that relating to electrons, that electrons are discrete, because some point in time it's like, well, something's got to be discrete and finite, and it's like classical and atomic, like we're classical to each other, and then it's like, well, electrons. It's like, well, they got to charge the mass ratio, right? It's like, yes, that's exactly what we use for everything. It's like, doesn't that just kind of vanish, and even the mass part of it just kind of oscillate, and that's why electrons move around, and that's why current kind of works, because the particles kind of have to give. There's waves through them or of them, one or the other. It's like, well, yeah. Yeah. But it's all related rates once we get it split out down to those. So those are the running constants again, is usual enough here. So, but Kelvin does make a great point about, like, yeah, it's infinite, obviously, because it's not finite, or else it would end. It's talking about wave motion and the octaves of light, and so relating like to the doubling and halving of octaves of frequency and wavelength, and the magnitudes and the orders of magnitude. And he describes instruments to measure the wavelengths of light. And then this is on the tides from Kelvin. So the tidal and tides and Coriolis and tidal forces is like the large outside nonlinear part, usually in a lot of approximations. So it helps show that then it makes the big potentials, and then those as they natural fall would have like rogue waves, but here's about tides. Tides. We have a true tide, depending on the sun, the mean solar diurnal tide, having first period, 24 solar hours, which is inextricably mixed up with those meteorological tides that I've just been speaking of, tides depending on the sun's heat, and the variation in the direction of the wind, and the variation of barometric pressure according to the time of day. Consequence is that in tidal analysis, when we come to the solar tides, we cannot know how much of the analyzed result is due to attraction, and how much the heating effect directly or indirectly, whether on water or on air, or on water is affected by air. As to the lunar tides, we are quite sure of them. They are gravitational and nothing but gravitational, but I hope to speak later of the supposed relation of the moon to the weather and the relation that has to the tides. So where there's a fall gravity instead, that's like, well, it's still kind of all point to point, the forces in the field of gravity, but then it's like shadows everywhere. So instead of like, if light has like a light cone, then gravity kind of has like a shadow cone. And so sometimes it's called umbral for the shadow, umbral gravity. So fall gravity, the idea here is not new, it's kind of put together new. After like Faraday and Lesage, or Lesage, but Lesage, the push gravity. After Newton's pull gravity, after the ancient dictum, what goes up must come down, straight up and down gravity, Einstein's gravity is just like, well, it's kind of a follow gravity. It's like whatever Newton says is kind of what it adds up to, which is what Kepler pointed out, and that's what it is for like celestial bodies. And so you can say that Newton's is a pull gravity, Faraday and Lesage is a push gravity, Newton or Einstein is a follow gravity, and then here it's a fall gravity, as to tombe, to fall, the fall gravity. And then Newcomb here is on the extent of the universe. So that reminds me of the guy who's like on the multitude of worlds. That's like 500, 600 years ago. The guy wrote a book. It's like, what about all the other planets? Are they full of life? And so on the multitude of worlds is a great little book because it entertains the idea that, yeah, they're everywhere. And of course, since today we know it's like, well, there's no way that anybody who's far, far away could ever get here because of light speed. And it's like, well, time, and the other thing too. So, introductory note. It's talking about See, Newcomb is from Nova Scotia, and brought him to Cambridge, Mass. He's professor of mathematics in the Navy. And then he went to Johns Hopkins, mathematical astronomy. He directed toward the explanation of the observed movements of the heavenly bodies. So there's Didonder to get figured out a little bit with regards to the geodesy. And the parameterized post-Newtonian is the way that it is. And then, let's see here. The wonder of the universe. As we make a feeble attempt to learn what science can tell us about the structure of the starry frame, I hope the reader will allow me at least fancy him contemplating it in this way. About Lyra and Aquila and these constellations, about there's many constellations and they vary a little bit, but over time they vary almost indistinguishably. But 15,000 years ago, Polaris was not our North Star. Polaris was pointing at a different star, and that makes a big difference when in terms of the ether, say that Earth spinning around the sun, spinning around its arm in our galaxy, the Milky Way, is part of, and that all be in one rotational frame, kind of by itself. I mean, galaxies are far, far, far apart in near empty space. Is the idea, because it's an atomic model, and it happens to line up, and according to the moments of those motions, the galactic scale of these things. That just kind of trails off into the idea that light speed is a constant, and its constant is like how fast we're going. The light speed rest frame theory is for the rest exchange momentum theory. These two together helping to, along with the classical mechanics and world's turn bit, solve the crises in modern cosmology with regards to dark matter and dark energy for our luminous matter and luminous energy. Why the theory is broken today, our premier theories today. One of the unities which we have described leads at once to the conclusion that the stars must be at very different distances from us. So he's helping go to explain, show it's not just one celestial sphere like at a fixed distance from us spinning around, because that's the usual classic idea. It's like we live on a globe. There's a globe of the stars. They don't move, and so it spins around its concentric spheres. He talks about standard candles. To do this, we must be able to determine the distance of a certain number of stars. This is the only way in which we can make a definite measure of the distance of any one star. From the time of Copernicus to that of Bessel, measuring the parallax of the stars. Then that gets into the theory of light and peripheral parallax and some other ideas here. They're usual. Once they kind of have to all be put together into a theory. That's like the Sumerian theories of the 3 different sections of the heavens or something. Knowing these proportions, we may. Observations of sufficient precision for this purpose were commenced about 1750 at the Greenwich Observatory by Bradley, then Astronomer Royal of England. But out of 3,000 stars, only a few are available. Ever since this time, the determinations made by each generation of astronomers have not been sufficiently complete and systematic to furnish material for anything like precise determination of the proper motions of stars. Well, it's been a while now. The Sky Survey is great. I mentioned Struve. Geographical Evolution by Sir Archibald Geikie, Geikie, or Geikie. Geikie was born in Edinburgh, Scotland, in 1835. It's part of the Geological Survey. Geographical Evolution, Modern Geography, right then. Contributions to nonlinear partial differential equations. So this is something that it was looked at a little bit here as part of descriptive differential dynamics. I'm just going to set this back aside, but as I was collecting this, I wanted to just refer to like the nonlinear or the non-standard is a very active research area, and particularly in statistics and probability, because it's always lying to people because they let it, because it's really about the classical and the linear, and then for Bayes' law, but for then discrete distributions which are closed, and then for the classical and then the continuous distributions which kind of get into the ideas here of how these things come together and go apart, and then about knowledge and expectations and uncertainty and chance, that it just reflects upon that probability is perhaps the field with the most active development of the non-standard, and what's to be the super standard is what's to be arrived at, because it still has real analytical character about the continuum analysis and the infinitary reasoning. That's just to mention that that's minus. Here's this book on Tom Paine. I'm just going to read that some more later, but that's not so much the relevance. Ancient Medieval Science During the Renaissance. Sarton, as a Rosenbach Fellow in Bibliography, is an exemplary account of how and to what extent ancient and medieval sciences were transmitted during the Renaissance. 1450 to 1600. So, the Galenic opera about Galen, about medicine, Camerarius of Bamberg held classical professorships at Nuremberg, Tübingen, and Leipzig. He had a number of Greek and Latin classics, was a great friend of Melanchthon, and a polyhistor. So he studies history of all sorts. For example, he's one of the many authors of books on comets. Leonhard Fuchs was perhaps less known than Camerarius, but he was a greater man, more original. Born in Wending, Bavaria, in 1501. So Fuchs and the Fuchsian is another part, like Fuchs and the Fuchsian and Phythian, which is actually his full name, Phythian. And like Dodonder and these ideas, like for Coriolis, are all relevant to the higher geometry for like Fritz London or somebody who's come up with some infinitary results. And so it's like, well, at least for some kind of global setting besides this local setting and the near field and far field, we have a way to point something back into it, line those back up. And so that's, of course, what is one of the great things that goes on all the time. Otherwise, that it's like our finite element analysis is too jaggy and doesn't work on the edges. De Anima, Historia Animalium, made by the elder Scaliger, Lyon, 1584. The Latin text of the De Partibus Animalium was printed with the scholia of Michael of Ephesus, I'll usually say Ephesus, in Basel, 1559, and the Latin text of De Generatione Animalium, so reproduction, is De Anima, biology. The Englishman was William Turner, who published a book on birds derived from Aristotle and Pliny, yet containing new observations of his own. In addition to books on birds, he also wrote an account of English fishes. Somewhere I have a great, a book on the fishes of maybe 100 years ago. Sadly, many do. The Great Extinctions, 1, 2, and 3, in rapid succession in the 20th century. No longer often found. Cecil Pino was born in Arezzo, Toscana, and studied medicine. So this is a lot about medicine. Natural history. Historia Mundi, Johann Froben of Basel. Franciscan Giovanni Riccucci of Camerino, who flourished in Padua and Vienna. Their edition of 1535 was revised by Sigismundus Galenius of Prague. He was one of the leading philologists of his day, Hellenist as well as Latinist. Greek and Italian, I suppose. Roman, say. The French translation of the Natural History by Antoine Dupinet was mentioned above, but before its first publication in 1562, a summary of books 1 through 16 was published in French by Pierre de Changy, Sommaire de Singularité de Pline, Extrait de 16 premiers livres, et mise en vulgaire François. the singularity of Pliny. That's something to follow up on, perhaps. Botany, the Almagest, the greatest, as it's put, is what it says. In Greek, Arabic, Latin, and Hebrew is too complicated to be told here and would sidetrack us. We might say that story is continually intermingled with the history of pre-Copernican astronomy. The Latin Almagest was not included among the incunabula, but Ptolemaic astronomy was represented indirectly, first by the Compilatio Astronomica of Alfraganus, 1493, second by the Epitoma in Almagestum of Regiomontanus, has been mentioned here before. And then we're getting up to Kepler sometime later, but, Kepler is familiar with all these things. Anatoly. Regiomontanus' Epitoma, published posthumously in 1496, was more important because he was very familiar with the Almagest, as I shall show presently, was a practical astronomer, the greatest of the third quarter of the 15th century. So, yes, the star lore and this kind of thing, and the cosmic survey, and all these kinds of ideas of that it's always been the only thing that was possible to really kind of do after the light of the day was done, and there was the light of the stars and the moon and its reflections. But that was, everybody's had the same picture, at least in the same hemisphere. And then there's, according to the Sumerians, the different sections of the sky. That's why the astronomy was so key for all such matters of it's related to cartography. It's related to lots of different things. That's the way it is. So, Gilbert, Tycho Brahe, Bacon, Harvey, the Italian Galileo, the German Johann Kepler. All of them were children of the Renaissance, which is where the Renaissance is like we're having ideals again, and if the Enlightenment is like we're having rationality again. And so the Renaissances and Enlightenments have kind of come around many, many times here. So you can kind of think of like the medieval Renaissance and Enlightenment, or the medieval Enlightenment, then there was a Renaissance, and then there was Enlightenment again. Or like the golden age of the Islamic era, before that, and then, quite before that, the Romans after the Greeks, and so Enlightenment is just associated with the logicist positivist tradition, and the Renaissance is associated with the idealist position. So they're making theories all in this Renaissance, and then breaking them down in the Enlightenment, and back and forth, and back and forth. My first lecture, Sarton says, I made a distinction between two kinds of men of science, the imitative and the non-imitative or creative. The distinction is incomplete and in many cases unclear. And so this is kind of reflects on these cycles or these things. At any rate, there was an intermediate type of men who were at once and at the same time antiquarians and naturalists. They might be editors, translators, commentators. Most of the time, you'll be capable of original reactions to natural problems. Well, yeah, it's hard to come up with something new, except to frame it in things that already exist. It's always possible to come up with something new. It's just whatever is. It's the moment in the spark. But yeah, coming up with something that's really not just old wrapped as new, or something that's really new, is that gets in things like the super classical. So like these thinkers working in the non-standard probability theory, they have two pieces and they know where it should be before and after. Because, for example, you can have a kind of a posterior account, but then to make for like, well, how can our inductive account attain to this posterior account? Because it cannot. It would be readily shown and demonstrable contradictory. It's like, well, that's the point of superclassical reasoning. So you better know Zeno and all his that stuff, and then you get up to things like wave-particle duality long after Fourier-style analysis and its superclassical development. And then for things like, well, what happened to the severe abstraction, the mechanical reduction that gave us all our successes today? It's like it chopped out all the round bits and left the pointy bits in a nice row. And we figure it's got to be that way, the linear, but it's unlinear, then it's nominally, and then it gets non-linear, and finally, also it's got to be back and be super linear again. And that's not to be related necessarily like linear superposition and stuff like that, which is a different idea from differential equations, and then the usual ideas of probabilities and superposition of states or the state vectors and these kinds of things. but it is intended to be like Poincare completion, and that it's continuous again, and these kinds of things. My account is oversimplified. The other qualification, irregular practitioners, surgeons, independent doctors. Was it not safer to follow Galen and Avicenna than to try something new? It's like, well, yeah, make them new. The statement that the Middle Ages were dominated by theology and the Renaissance by philology may suggest another objection. Was not the 16th century the age of the Reformation and of the Counter-Reformation? Did it not witness spiteful controversies, merciless persecutions, and religious wars? It was a golden age for theological pamphleteers, but in spite of that, or because of that, it was an age of growing disillusion and doubts of intolerance. And the Counter-Reformation here was, in the time of Galileo, was a great step forward towards scientific rationality. So the Counter-Reformation was after Martin Luther's in the Reformation, that kind of retreated from like some of the things attributed to like the causal, and then part of the aspects of Urban VIII and Galileo and the Counter-Reformation was actually stepping that forward, the scientific part. We have finally learned from bitter experience that persecutions do not strengthen religion but weaken it and may end in destroying it. Theological pamphlets fail to dominate public opinion but help to divide it. Intolerance is as different from religion as jealousy from love. So religion can also be for like dogma in science more generally here. Intolerance is as different from religion as jealousy from love. There's innocuous jealousy, and then there's mean jealousy, or the monster of jealousy. And there's a tolerance, and you know, just intolerance is being unaccepting, and then there's indifference. It's like, well, I don't really care, you know, either way. So yeah, these are again like, you know, like the electron charge to mass ratio or something like that. It's like, well, it's a constant, it's linear, it's an invariant. It's like, well, yeah, but I'm not going to be broken by it. You know, these kinds of things. Copernicus and Vesalius. All right. So anyways, that's some of the contents of that and its relevance. Okay, into the box. What is in this box? If I find something and it's just inappropriate, I just will not get it. But I think these are all plenty appropriate. Mathematics from the Birth of Numbers by John Goulburg, if I'm not pronouncing this incorrectly. Yeah, John Goulburg. This gently guided, profusely illustrated grand tour of the world of mathematics takes the reader on a long and fascinating journey. From the dual invention of numbers and language through the primary realms of arithmetic, algebra, geometry, trigonometry, and calculus, to the final destinations of differential equations with excursions into symbolic logic, set theory, topology, fractals, probability, and assorted other mathematical byways. Mathematics from the Birth of Numbers is unique among popular books on mathematics in combining an engaging, easy-to-read history of the subject with a comprehensive mathematical survey text. So it's to be kept in mind here that there's a deconstructive account. So some of the things that are kind of like, well, these have always been together and put together, has it like, well, be sure and take them apart, because the algebraist view of the number theorist view of geometry, or the geometry's view of number theory, has that algebra is just kind of abstraction, and so geometry and number theory are each their own thing, like from the space of words or in the space of points. And so then, and also that arithmetic is broken down at least 3 different ways, but at least 2, division and addition, besides having those all just be like repeated, inverse, repeated, and inverse. That's just to say that's kind of an approach compared to this. Oh, getting into indeterminate limits talks about L'Hopital's rule. And then we get into something like Rodriguez formula, or maybe either way, from Rodriguez formula to L'Hopital's rule. Hadamard's and Della Valle Poisson's prime number theorem. Geoffrey Hardy about the Riemann function, reduction formulas. This gives a lot of great methods, differentiating algebraic functions. Here's got some snapshots of the method of fluxions in infinite series by Newton. And there's Huygens and then about the analyse des infiniment petits pour l'intelligence des lignes courbes. Wow. So these are like the works in analysis. Geometria indivisibilis continuorum by Cavalieri. So this is Cavalieri, kind of right before the time of Galileo, was the infinitesimal analysis of the school. It says, here's the remarks on the calculus. Pythagoras, Zeno, Platon, Eudoxus, Euclid, Archimedes, Pappos, Kepler, Galilei, Torricelli, and then Cavalieri. So that's mostly Archimedean, and then Cavalieri. For Xenocrates, besides Eudoxus, and then also things like Gross test, and De Continuo and the Mertonians, De Roberval, Descartes, Renes. So yeah, this is it's through a lens, it's through his experiences, but it's really a quite wonderful and great collection of things. Sierpinski, that being the concrete mathematics, pretty much. Inverse trigonometric functions, a bunch of different identities, geometry and shapes, units of measurement, and then where it gets into, what does it kind of get into? Differential equations, differentiation. We'll see kind of how he ends. Second order ODEs. All right. And those are used for like all the Laplacian and all kinds of things, for the whole partial half account after Laplacian. Theory and applications of active devices. Skalnick, Krauss, and Reich from Van Nostrand. So active devices are not passive devices. They're electrical devices and electrical circuits. So a passive device is a resistor, a capacitor, or an inductor. And with regards to a resonant circuit, you could say that, well, those are kind of active circuits by the time you put them together as a device, vis-a-vis just the RLC theorems and formulas, Ohm's law, and then for Kirchhoff's law, active circuits. So this is the Van Nostrand series in electronics and communication, vacuum diodes, switching, electrical conduction in gases, graphical methods for things like the ways to calculate things, which are not like so. Resistors, untuned power amplifiers, tuned power amplifiers, and harmonic generators. So this gets into the resonance circuits and these kinds of things. With regards to, the open and closed resonance circuits and the shorts and the different quantities that get related in computing and putting them in algebra and putting them in formulas. Measurements of parameters. Various parameters can in principle be measured directly for a given operating condition by the application of a small alternating signal and the measurement of the appropriate quantities. When the parameters of an active device are measured, one of the ports must be either short-circuited or open-circuited for alternating signals, but the direct voltages and currents which establish the operating point must be maintained. So that gets into the whole like observer effect and this kind of thing. But mostly that's because observation, sampling, and measurement has its sampling is interference itself. So yeah, then it's usually just defined into circuits these days is like, well, design everything so also it has a secondary trace lead out to the JTAG board or whatever it's called. The idea of like the debugger pads. So then you could just kind of like tap those and then get an idea of what's going through it. And that it is. But I don't know so much about that, but I've been studying operating systems and design and these kinds of things. So this has got a lot of great and practical stuff. And okay, the multi-stable and circuits. So you might want to consider how to try to approach that with like higher mathematics, and that's kind of the idea here of the resonance theory and wave theory Parallel resonator negative resistance oscillators, about oscillators and antennas and dissipation and this kind of stuff. And the spiral waves. Here that's kind of being addressed as like, well, we kind of need a model of spiral waves because this is all a model of current and flow, and then as regards to that being just an integral as it flows and these kinds of things. But then as regards to, the inductors and all the circuits, like, well, that's waves. And it's all signals and waves, multi-frequency oscillation. That wave theory is very ubiquitous. Input voltage, output voltage. So this gets into things like, the Bruchla circuit and the idea of a Fourier-style approach to power regulators. That's what I've been thinking about trying to figure out a little bit. Some minutes left. So what is today's talking about? Well, it's really kind of reading from Helmholtz and Faraday a little bit. Well, this comes with the thing here. It's got a little poster. Oh, good. I was looking for one of these. This is the nucleons, originally prepared by G. Friedlander and M. Perlman, revised by J.R. Sten of the Knowles Atomic Power Laboratory. Gosh, I hope this book isn't radioactive. What is this here? So it's kind of like an atomic chart of it's a chart of the nuclides. So everybody's familiar with the periodic table of elements. But this helps show that the nuclides kind of grow like this. So at a given time and place, this is the chart of the nuclides, revised 1952. So yeah, the nuclear theory has both nucleons and hadrons. They're different things like this. So this is from Publications in Nuclear Physics. So here we've been reading a Sachs on nuclear physics. And then this is E.B. Paul from Wiley Inner Science. Nuclear and particle physics. Two different theories, nuclear and particle physics. Because nuclears are basically like inside the thing. It's like one time as work we were discussing anything and we were talking about blood. He's like, blood must stay in the body, It was like, blood stays on the inside. And it's like, similarly here with particles, it's like, well, nucleons aren't particles. They're inside the nucleus. 1969, North Holland Publishing Company. John Wiley and Sons. When a student reaches an advanced stage in his undergraduate course and decides to specialize in nuclear physics research, he finds himself faced with the formidable task of absorbing a vast number of new concepts, new facts, and new techniques, particularly the quantum mechanical tools specific to modern nuclear theory. This task is best begun with the help of good texts written by scientists who are actively pursuing research in the field and who are able through clarity of mind and ease of expression to overcome many of the students' difficulties and inhibitions. There are not many textbooks of recent date satisfying these requirements. The present volume fills this need. The broad scope of Professor Paul's text is clear from a perusal of his chapter headings and subsections. The inclusion in the book of the results and interpretation of current research in high-energy physics is timely. At the moment, the pure nuclear physicist has little chance to grasp the relevance of discoveries made with the help of modern high-energy accelerators, and he finds it difficult to appreciate the bold ideas put forward by the theoretical physicists. It is a great pity for him to be deprived of the excitement of these developments. I feel this book will help the student to bridge the gap between nuclear and elementary particle physics, technically and conceptually so very different, but nonetheless closely related through their common interest in the origin of nuclear forces. So, I'm just glad that the preface author here, he makes a point to make clear that these are things. E. Brettscher, Bretschcher. So, I'm not going to get into this at the moment, but much like Sachs' theory of 15 years before that, this is nuclear and particle physics. The Inflationary Universe by Guth. Well, I don't need this anymore. I mean, Guth might have a perfect eidetic memory, but his sombrero approach to as a numerical method can be used for a bunch of different things too. But the inflationary cosmology and then the expanding universe is like, well, we got a crisis today in physics, and though there was 80 years of great success, now it needs to be kind of redone. So But that's a pretty good book about the story of the 80s and 90s and expansionary cosmology. And Guth has sort of, he's one of those people with eidetic or photographic memories, or so he describes it. And so, I mean, that's good, but at the same time, it's not saying much anymore. This is Henry Miller, Tropic of Cancer. Won't be needing to read that at the moment. I've read that before. He went to France and was kind of bohemian, and it's just the story entails of a wild young man and all those things. Some people think it's a comedy. Some people think it's angst. I don't know. I don't know what it is. The Restless Universe by Max Born. So this is back to physics, and Born is he ends up describing the things about, like, well, if it's meters per second or seconds per meter, it can't be both. Yet if we don't have both, then we can't do mathematics. So somehow it's always restless. The universe, it quivers, yet there's nothing at rest. And then it's like, well, what's the Born law? Is like, well, this is just part of quantum mechanics that says it has a center and it's at rest. It's like, well, so on the one hand, you write this whole book about, it's like, it's all over the place, and at the other end of the day, people say that the law is that's basically one of the primary things with Pauli principle that makes quantum mechanics, physics, what it is today. It's like, well, it's like, so it's like, well, yeah, we can't think that. This is philosophy, this is physics. They're two different things, and it's like, well, they're not, Gets into Lyman and Balmer and this kinds of things. So Lyman is basically like, it's like, well, it's starting to have the spectrum. It's diffracting, and the Balmer is like, everything goes up after that. But it really is like, well, that's just a second order, and then there's third, fourth, fifth, sixth, and any number of unnamed orders that go on up the infinitary for it to get around. Bohr's, Zeeman, Sommerfeld. These were contemporaries of Born. Rutherford, who was a little bit before, Rutherford is pretty great. Rutherford leads more into like the nuclear theory. This is more into the particle theory. Formation of atoms, structure of known nuclei, gets up to beryllium, storehouse of creation, de Broglie's matter waves of different kinds. So it's got electrons and positrons. And so it's got a good little survey here of a bunch of this kind of stuff. Getting into like, the carbon rings and these kinds of things like chemistry and this. The spin of electron. The chief result of this method and other less direct methods is that the proton has exactly the same spin as the electron. So that's what it is about. When the question of a new edition of this book arose, I felt a considerable embarrassment. To bring it up to date, I had to write an account of the scientific development since 1935. But although this period is as full of fascinating discoveries, ideas, theories as any previous epoch, I could not possibly describe them in the same tone in which the book was written, namely in the belief that a deep inside the workshop of nature was the first step towards a rational philosophy and a worldly wisdom. It seems to me that the scientists who led the way to the atomic bomb were extremely skillful and ingenious, but not wise men. They delivered the fruits of their discoveries unconditionally in the hands of politicians and soldiers, thus they lost their moral innocence and their intellectual freedom. Therefore, I have to apologize that the following account is short and dry. Its purpose is not to raise enthusiasm, but describe how the present tragic situation has arisen. So, then he's talking about Sommerfeld. Now, I have another copy of this book. I have like the first edition of this book somewhere, but this is basically just about apologizing for the bomb. And then he ends with some nice poesy. He talks about nuclear structure and nuclear physics in the end, kind of like that book, Nuclear Physics and Particles. All right, so book 2 has begun. Thanks for watching, gentle readers. I hope this will be some use to you, and it will so proceed at some point in time later. So this is then today about nuclear particles. So long.